Greetings, Earthlings! Welcome to my new channel, Alien Logic, a channel dedicated to math, science, and logic. In this video, we're going to be covering the Sleeping Beauty problem. This is a logic problem that is currently considered unresolved. It's caused a great deal of controversy online and even in academic circles. What follows in this video is my attempt to explain the Sleeping Beauty problem and my attempt to solve it once and for all. So, without further ado, the Sleeping Beauty problem. For those of you unfamiliar with the Sleeping Beauty problem, here's how it goes. Sleeping Beauty agrees to participate in an experiment. She goes to sleep on Sunday night and an experimenter flips a coin. If the coin lands heads, Sleeping Beauty is woken up on Monday, asked a question, and then takes a drug that puts her to sleep and erases her memory of that day. She sleeps all day Tuesday, and on Wednesday she wakes up and the experiment's over. If, however, the coin came up tails, she's woken up on Monday, asked the same question, and takes the same drug that erases the memory of that day. But then she's again woken up on Tuesday, asked the same question, and takes the drug one more time, erasing her memory of that day as well. Again, as before, the experiment's over on Wednesday. The question Sleeping Beauty is asked is the same question we need to answer. What is Sleeping Beauty's credence that the coin landed heads? Credence is kind of a fancy way of saying probability. So, from Sleeping Beauty's point of view, what's the probability that the coin landed heads? One answer to the question, and a common answer, is 50%. Coins have a 50% chance of landing heads or tails, assuming it's a fair coin, and so that's probably the right answer, right? But there's another point of view that claims that the coin only had a 1/3 chance of landing heads. The traditional explanation of the Thirdian point of view is a little bit tricky, so I'll do my best. Basically, it asserts that from Sleeping Beauty's point of view, there's an equal chance of her being in each of the 3 awake states, and she doesn't know which one she's in. It asserts that from her point of view, if she knew that it was Monday, there would be an equal chance of it being after a heads was flipped or after a tails was flipped. Likewise, if a tails was flipped, there's an equal chance that it's Monday or Tuesday. Since all 3 probabilities are equal, there must therefore be a 1/3 chance of her being in each of these states. But I think there's another explanation that can make the Thirdian point of view a little bit more intuitive. Imagine Sleeping Beauty did the same experiment, but many times in a row with no break in between. Now, when she's asked on a particular day, did the coin land heads or did the coin land tails, she knows she's going to be awake twice as many times after the coin landed tails. Therefore, from her point of view, there's only a 1/3 chance that the coin landed heads on any particular day when she's asked the question. Which answer do you think's right? It's a pretty difficult problem that's caused a lot of disagreement for a number of years. I'm about to give my answer to it, so if you want, go ahead and pause the video and come up with your own solution. And in a moment, I'll continue with my solution to the Sleeping Beauty problem. The way I'm going to approach the problem is I'm going to try to create an analogous situation. Rather than using a person, I'm going to use an AI. Assume an AI smart enough to make basic probability calculations and also smart enough to answer basic questions. Likewise, rather than giving it a drug, I'm going to go ahead and make a backup copy of it. If you think about it, resetting to a backup copy is basically the same thing as erasing a person's memory for one day. In our AI equivalent Sleeping Beauty problem, the experiment's going to run like this. We're going to flip a coin, and if it's heads, we're going to turn on the AI and then ask it a question. If it's tails, we're going to turn on the AI as before, ask it the same question, turn it off, and then turn on the copy, ask it the same question, and then turn it off. Assume the AI is aware of and understands our test procedure and probability as well. Also assume the AI is aware that a copy of itself may have been made, but will be unaware whether it is itself the original or the copy. If you think about it, you should realize this experiment is effectively equivalent to the experiment we're performing on Sleeping Beauty. The way we're going to solve this problem is by starting with much simpler problems and gradually working up to the problem we're trying to solve. Imagine a much simpler experiment. We're going to flip a coin, and if it lands heads, we're going to turn on the original AI and ask it, was it heads or tails flipped? Likewise, if a tails was flipped, we're going to turn on the copy and ask it, was it heads or tails flipped? Well, the AI doesn't know, therefore its answer is going to be 50% chance. There's a 50% chance a head was flipped, and it's the original, and a 50% chance that a tails was flipped, and it's the copy. And the AI doesn't know which is which. What's interesting about this is from the AI's point of view, it doesn't really matter if you flip the coin or not, and it doesn't really matter if you turn on the copy or the original. Once it knows that a copy was made, or potentially made, it's aware that there's a 50% chance that it's the original and a 50% chance that it's a copy. The two situations, from the AI's point of view, are identical and indistinguishable. Now let's consider a second experiment that's a little more complicated and a little bit closer to the original question. This time we're going to flip a coin twice. The first coin flip will decide whether or not a copy is made. If a heads is flipped, a copy is not made. If a tails is flipped, a copy is made. The second coin flip will decide which AI we're going to interview. Now, of course, if no copy is made, in all cases we're going to interview the original. But if a copy is made, then there'll be a 50% chance we're talking to the original and a 50% chance we're talking to the copy. If the AI is fully aware of this experiment, it's going to calculate that it has a 75% chance of being the original and a 25% chance of being a copy. Further, it will know that there was a 50% chance of each coin having landed heads or tails. We're now ready to take on the Sleeping Beauty problem using an AI rather than a person. But remember what I said about making a copy of an AI. If the AI believes or suspects a copy has been made, it will give equal credence to it being the original or the copy. It doesn't matter if I turn on the original, turn on the copy, turn on them both, or flip a coin to decide which one I turn on. The AI will not know and give equal credence to both possibilities. Now in this experiment, I'm going to flip the coin one time. If it lands heads, I'm not going to make a copy of the AI. If it lands tails, I'll make a copy of the AI. I now ask the AI, what is the probability it's the original, and what is the probability a heads was flipped? Well, there's a 50% chance that a heads was flipped and no copy was made. There's a 50% chance that a tails was flipped, and in that case it will give equal credence, 25% chance each, to it being the original or the copy. And this is the correct answer to the Sleeping Beauty problem. I think this approach to solving the Sleeping Beauty problem is useful because it makes it clear that a particular AI will only be asked a question one time, whether it's the original or the copy. Whereas in the original Sleeping Beauty problem, it's kind of confusing because Sleeping Beauty is going to have two chances to answer the question if a tails is flipped. And in fact, that's the core problem. It is difficult to disentangle the fact that Sleeping Beauty is going to get two chances to answer the question in the case of a tails being flipped, and I'll be covering that in the next section. Imagine Sleeping Beauty were to earn $600 each time she correctly guessed if the coin landed heads or tails. In that case, her correct strategy would be to guess tails because, effectively, she would get two chances to be correct, whereas with heads, she would only get one chance to be correct. The expected profit from guessing tails would be $600, and the expected profit from guessing heads would be $300. Also note, Sleeping Beauty should be able to calculate this expected return both before the experiment begins and while the experiment is running. And also, in each case, she should come to the same conclusion. This example is useful because it exposes a hidden assumption in the Thirdian logic. That hidden assumption is, all correct answers should be given equal weight. And if you give equal weight to each correct answer, then yes, there's a better payout by guessing tails. You get two chances to get $600 versus one chance. But when you look at any one answer, you'll see that each answer only has a 50% chance of being correct. Still not convinced? Well, I think I have a final argument which just might do the trick. It may not have occurred to you, but you can actually do the Sleeping Beauty experiment at home with no need for exotic drugs or technology. Well, one day of the experiment anyway. All you need is pencil, paper, a coin, and a friend. Here's how it works. One person's going to play the test subject and one person's going to play the experimenter. The experimenter's job is to, in secret, flip a coin and record the results. The experimenter is basically creating a test regime that we could put a real-life Sleeping Beauty through. In this case, we're going to start with what I call an extended Sleeping Beauty experiment, where our imaginary Sleeping Beauty would go from one test to the next with no break in between. As a result, she wouldn't know what day it is or how many coin flips she's gone past. Then the experimenter is going to translate the coin flips into an actual test schedule, as I show here. For example, in my case, first I flipped tails, so day 1 and 2 are tails. Then I flipped heads, so day 3 is heads, and that's the second coin flip. Day 4 and 5 were tails, and that's the third coin flip. Day 6 and 7 were tails, and that was the fourth coin flip. Day 8 was heads, and that was the fifth coin flip, and so on. You've now created a test schedule that you could, in theory anyway, use in an actual test, so long as you keep it secret from the test subject. How do you simulate a single day? Well, that's easy. Just pick a day at random, don't tell the test subject what day it is, and then ask them if a heads or tails was flipped. We're closing in on the final explanation now. If you select a day at random, giving each day equal weight, in fact, there'll be a 2/3 chance that that day will be after a tails flip. Just take a look at the chart right here and it's pretty clear. So you might think, victory for the 30ans, right? Not quite. Imagine instead we selected the day by first randomly selecting a coin flip and then randomly selecting a day within that block of days. In that case, you'll see there's an equal number of heads and tails on this chart. Therefore, there's a 50% chance it'll be a heads block and a 50% chance that it'll be a tails block. And that's the key to solving the Sleeping Beauty problem. Sleeping Beauty knows she's localized in the first block. In fact, it wouldn't have to be the first block. All the experimenters would have to do is select the block in advance, tell Sleeping Beauty which block she's in, and then run the experiment, and then it would change the probability to 50%. So the reason the correct answer to the Sleeping Beauty problem is 50% is because Sleeping Beauty knows she's localized in the first block, or she knows she's localized after a single coin flip. Pretty neat, huh? Hey, thanks for listening to my first video. Like, share, subscribe. Hope to make more videos in the future and see you soon. Thanks a lot.